Hello everybody. So in this video we are going to start the applications of what we mentioned in the introduction, which is the mass balance calculations for reactive systems. And what we will cover here is the methods that we can use to do the mass balance in case of reactive systems. And we have three methods that we can use, which are mentioned in the textbook: the atomic species balance method, the extent of reaction method, and the molecular species method. In the syllabus we cover the first two methods, and I believe they're enough. They can, or one would be enough. But anyways, they are two different methods that we can use for solving different problems. Each one of them has pros and cons, and this is something we will mention when we go through them in details. The atomic species balance method is going to be kind of new method. The extent of reaction is almost covered in the previous video, and I believe we covered everything except just the degrees of freedom analysis. Other than this, we already covered everything regarding the calculation. So this is going to be kind of repetition of what we mentioned before. So the point that I want to start, I like to start with, is the very first point that we started this chapter with, which is the mass balance method, and or mass balance equation, the general mass balance equation. I like to keep repeating this, that we are still doing the same thing. It's all about mass balance and the conservation of mass, and it's just how we can express this in form of equation. So in case of a steady state, we said the accumulation is going to 0, so the equation would be input plus generation minus output minus consumption equals to 0. And in under steady state conditions, the accumulation would be 0. In the atomic species method, the main idea or the main philosophy of this method is that we do balance on, as the name says, the atomic species, meaning that you have the element. It's present in more than one compound in the in the system. So you can have oxygen in water, you can have oxygen in methanol, in ethanol. All of them contain oxygen. So we do balance on the atomic oxygen, and we said before that when we do a reaction, one of the main things that we need to check in the very beginning before we start doing any calculations regarding the reaction is the balance of the reaction. And we said the balance of the reaction means that the number of atoms of any element in the feed is equal to the number of atoms of the same element in the product. So this is something that we have to keep in mind. So in this case, if we are doing the balance on atomic species, then there will be no generation and there will be no consumption, because generation and consumption is the change in the number of moles of a compound due to the chemical reaction. And what happens is that the atoms change their place between different compounds, but still the number of atoms is always going to be the same. The number of atoms is always going to be the same. So comparing the feed to the product, of course. So in this case, we have no generation and we have no consumption because the number of atoms is always going to be the same. So the equation will end up to be input equals output. Of course, it's the same shape of the equation that we used in the non-reactive system, but this is going to be different regarding the calculations, and this is what we will see in the coming slides. It's important here, and this is one of the main differences between this method and the extent of reaction method, is that we don't take the extent of reactions into considerations in the calculations and in the degrees of freedom analysis. And this is a very, very important thing. So here we don't really care about how many reactions are taking place and what are the compounds that are involved in each one of the reactions. We don't care about all these things. We just care about what goes in and what goes out and comes out of the unit, and we have to know precisely the molecular formula of all the compounds in the system, and this would be and demonstrated in this example and the next example. So in this example, we have a stream that contains 5 compounds: oxygen, nitrogen, carbon dioxide, water, and methane. And we know the flow rates, or the number of moles of each one of these compounds, and we want, and if we look at these 5 compounds, we have the elements, or the atomic species that we have is oxygen, nitrogen, we have carbon. Oxygen is already there, we mentioned oxygen before. Hydrogen, we also mentioned oxygen. Carbon was mentioned here, hydrogen was mentioned before. So there are only four elements, or 4 atomic species. And we can calculate the number of moles of each one of these atomic species. And for example, for oxygen, or let's take it, start with carbon. So carbon, we have carbon in carbon dioxide and in methane. So if we want to calculate, it's not a balance on carbon, it's not the right word, but if you want to calculate the number of moles of carbon in the mixture, then it's going to be 20 moles, and each one of these moles contain 1 mole of carbon, and 18 moles, and each one of these moles contain 1 mole of methane, of carbon, I'm sorry. Okay, so it's going to be 20 times 1 over 1 plus 18 times 1 over 1. I put the units just to demonstrate how we do the calculations, and we already did this, I believe, in chapter 3, if I'm not mistaken. That we did this in chapter 3, and we were able to calculate the number of atomic carbons, or oxygen, or whatever. So this is very straightforward thing. So it's I believe it's not a big deal. For hydrogen, we have hydrogen in water, and we have hydrogen in methane. So it's going to be 30, but each one of them contains 2 hydrogen atoms, so it's 30 times 2, and 18 moles of methane, and each one of them contains 4 hydrogen atoms. So we have 30 times 2 plus 18 times 4, so this is 132 moles. Then for hydrogen, oxygen, we have oxygen in O2, in CO2, and in H2O. So it's going to be 70 times 2 plus 20 times 2 plus 30 times 1, and then the result would be 210 moles. And finally for nitrogen, it's only in N2, so it's 278 times 2. So this is how we calculate the number of moles of each one of the species, of the atomic species, in a stream. So what we are going to do is we will say that the number of moles in the feed stream equals the number of moles in the product stream, and we will have an equation that contains some variables that we can calculate. But this is how we calculate the number of moles. So for the degrees of freedom, the degrees of freedom is going to be very similar to what we used to do before, but we have to be careful when we do the degrees of freedom analysis for a reactive system, when we do the balance using the atomic balance method, because there is one big difference between this degrees of freedom and what we used to do before. In all the systems that we mentioned before, for separators, for mixers, for whatever, we said that the number of moles is or the number of equation is equal to the number of compounds, or number of species that we have in this system. So this is something that is very important to notice. And for example, if we have this same stream in or a feed to a unit, and we have only these 5 compounds for non-reactive systems, of course, then we will say that we have 5 equations. I will have 1 equation for oxygen, 1 for nitrogen, 1 for carbon dioxide, 1 for water, and 1 for methane. This is how we do or set the number of equations. But in this case, you would see here the number of equations is equal to the number of atomic species, because we do or write an equation for each atomic species. So we have to be careful here. The number of equations is not equal to the number of compounds, it's equal to the number of atomic species involved. So you have to count the number of atomic species well. Okay. or the number of elements, if you want to put it this way. So for the reaction, we don't put anything to account for the reaction in the degrees of freedom. So we still have the equation, which is the degrees of freedom, number of variables minus number of given variables, and these two are the number of unknowns minus number of equations minus number of additional relations. So this is the part that would be different, which is how many equations that we have. So let's see this example here. It will make things clearer. We have ethane is dehydrogenated in steady state continuous reactor according to the reaction. So it's the ethane dehydrogenation to produce ethylene and hydrogen, and we have the feed is pure ethane, so it's 100% ethane with a flow rate of 100 kilomoles per minute, and we know that the conversion of ethane in the reactor is 60%, and we need to calculate the product flow rate or the components flow rates in the product, and we have this flow sheet that is drawn here. We have 100 kilomoles per minute of ethane in the feed, and we don't know anything about the product, but we know something. We are told that the conversion is 60%, so we know that there are some of the ethane that is not produced, is not consumed, which will come out as an unreacted ethane. And we have also the products, which is a result of reacting of 60% of the ethane, so it's going to be ethane, ethylene, and hydrogen also. So we know that these three compounds would be in the product, even if we are not told that. So let's start with the degrees of freedom analysis. For the degrees of freedom analysis, we have number of variables is 1, 2, 3, 4. So we have 4 variables. The number of given variables is 1. So we have 3 unknown variables, which are these 3 flow rates. The number of equations is equal to the number of atomic species. We have carbon here and hydrogen. There is no other compounds that are there. So it's I mean atoms or elements or atomic species in the system. So it's only 2 equations, and we have one additional relation, which is the conversion. So the conversion is, we know it's a relation between the number of moles of ethane in the product and in the feed. So it is a relation between 2 variables in 2 different streams, the ethylene in the feed and ethylene in the product. So it is one additional relation. We have also examples of the additional relations that are very common in the reactors is the yield and the selectivity, because all of them are relations between some of the variables with others. So this is the number of additional relations that we have is 1, and so the degrees of freedom is 0. So it means that the system is solvable, and we can calculate the unknown flow rates. So again, we have 3 unknown variables, which is 4 minus 1, and we have 3 equations to use, the additional relation and the 2 balance equations. So just for the sake of demonstration now, I'll start with the balance equations. So we have an equation for carbon. For carbon, we have 100 moles. Each mole contains, or kilomoles per minute, each kilomole of them contains 6 moles of hydrogen, of atomic hydrogen, of course. And the product, we have number of mole of ethane that we don't know, multiplied by 6, because this is the number of hydrogen atoms per mole. And the same for hydrogen, we have number of moles of C2H4 ethylene, multiplied by 4, and the number of moles of hydrogen multiplied by 2. So we will have here an equation that contains 2 unknown variables, which is the number of mole. I'm sorry, this is carbon. I'm sorry. What I said was hydrogen. This is hydrogen. It is 100 multiplied by 6, and then we have 6 times number of moles of ethane, and 4 times number of mole of ethylene, and 2 times number of mole of hydrogen, which would be an equation function of the 3 flow rates. For carbon, we have 2 times 100, 2 times number of moles of ethane, and 2 times number of mole of ethylene. Okay, I put the units in details just to demonstrate how these numbers are put, and to see that at the end of the day, after simplifying all these multiplications, they will all be kilomoles of carbon per minute, and these will all be kilomoles of hydrogen per minute. So now we have 2 equations and 3 unknowns, and we need one more equation solve these or to find the unknown variables. And this equation is the additional relation, which is the conversion. The conversion is the number of moles in the feed minus number of moles of the product over the number of moles in the feed, which is something we mentioned before. And this is equal to 2.6. So the number of moles of C2H6 in the product is going to be 40 kilomoles per minute. Now we can substitute in the first equation to calculate the number of moles of ethylene, and then we can calculate the number of moles of hydrogen, which would be 60 and 60 kilomoles per minute, or the molar flow rates. So this is simply how we can do the atomic balance method. Again, it needs only some attention when you do the degrees of freedom analysis, especially if you have a big flow sheet and you have more than one unit, and in this case you have to be careful when you put the number of equations, because the reactor is a special case. So you have to be careful when you put the number of equations, which should be equal to the number of species. So I'll stop here, and next time we will discuss the extent of reaction method, inshallah. So I'll see you then.